Well, hello everyone. We are moving on to our second topic from section 3.2, polynomials. And we're going to look at what we describe as end behaviour. We're also going to look at how to make pretty basic sketches of polynomials. So nothing too big. And then continuing from the sketching idea, we then move on to how to do a kind of more formal sketch of a polynomial, essentially. So what is end behaviour? Well, let's take a polynomial trying to explain to you. There's a polynomial, what the end behaviour is. Essentially, the end behaviour, and we describe it like this. It's a limit as x tends to infinity of this guy. So what you're trying to find out is, what does this function, this cubic function, how does it behave at the extreme values of x, at the very large million, and negative million. And we describe it with this. This is the limit as x tends to infinity. So that's like saying, what would this expression equal as x becomes positively infinitely large? And the answers that you can typically get from a polynomial, at least, is infinity, or you can get negative infinity. So it's a pretty, 50-50 chance of what it's going to be like. So how do we do it? Well, first thing you do is you only really need to pay attention when you're trying to find the end behavior, the limit as x becomes really big and positive. You only need to find, for a polynomial, what that guy is equal to. And the method we're going to use is a very primitive method. It's called brute force. You essentially make x infinite. So it's 2 times infinity cubed. Now, don't think of infinity like 5 or 45 or some number. Think of it as just a really, I have to say infinity without using the word infinite, but a really infinitely big thing. So if you take an infinitely big thing and you multiply it by another one of them and you multiply it again, what you get is 2 times an infinitely large number. And if you double an infinitely large number, you still get a positive infinity. So the end behavior of this guy, the end behavior is it goes plus infinity. We don't normally put the plus in. So how can that be of use to me? Well, it basically tells me that as x gets bigger, the y value gets bigger. And so if x gets infinitely big, the y gets infinitely big. Now let's go the other direction, because you can have end behavior at the other extreme. So this would be, what does this function look like going that way? Well, the limit as x tends to negative infinity of 2x cubed plus 4x take away 1 behaves the same as this guy. And that's 2 times negative infinity cubed. Now, negative infinity times negative infinity times negative infinity gets you negative infinity. And doubling negative infinity, you still get negative infinity. So the end behavior of this guy is negative infinity. And that looks something like as x gets really big and negative, the y value gets really big and negative. So it means that the curve looks like that. So what I now know is that if I was going to sketch this thing, I know that at the extreme ends, it's going up the way and down the way like this. And then what does it do in the middle? Well, it does what all polynomials do. They go up and down. You have little hills and valleys, sometimes 2 hills, sometimes one, well, who knows, sometimes 8 hills. But at least we know that regardless of the number of hills, it's going to go like this. So let's just do some more practice at calculating end behavior. So suppose I have a function 2x to the 4, take your x squared, and I want to know its end behavior. And I want to know both end behaviors. Right? And let's just call these f of x. That way I don't need to write this down. Now this is going to be the limit as x tends to infinity of that guy. And that's going to be 2 times infinity to the power of 4. Positive infinity times positive times positive times positive infinity gets you positive infinity, and doubling positive infinity gets you infinity. Let's see what happens this time. Well, you're going to get 2 times negative infinity to the power of 4. This you have to be a bit more careful. Negative infinity times a negative infinity times one more again. Even number of negatives multiplied together makes the answer positive, so it's positive infinity. And so positive infinity. That means that this function, this polynomial, if you do very big values of x, so the extreme values of x this way, the answer is plus infinity. But if you do very big values but negative, it goes like that. So this function does like that. So it probably end up looking like that. This one here would probably look like that. Now, if you want to say, well, how can I just ignore that x squared or get rid of it? Or in this case, ignore the 4x, take away 1. Why does that actually work? Because you might think, well, that might have an effect. Well, the effect it has is negligible compared to the biggest power of x. So let's take this guy. Let's suppose x is 1,000,000, right? 1,000,000 to the power of 4 is basically 2,000,000,000,000,000,000. Kind of like the American debt. Now, 1,000,000 squared might seem, and it is big, but 1,000,000 times 1,000,000 millions is nowhere near as important as 1,000,000,000,000,000,000 of them. It's one very small, insignificant part of it. So it's never going to overwhelm this answer. Only the biggest power of x takes predominance. It's the thing that matters. So that's helpful because if you can see from these calculations, the answer is going to be plus or minus infinity when you are talking about the end behavior of a polynomial. But not only is that true, right? You can see that there's not many choices. Now, this one here is a little bit sneaky. So I'm going to do the extreme. The limit as x tends to infinity of this function. And I know that we can simplify the problem to finding what that guy is equal to. Now I'm going to do the brute force. It's negative 2 times infinity cubed. Now infinity times infinity times infinity gets you positive infinity. And negative 2 times a positive thing will get you negative infinity. So on the right-hand side, when x is extremely large and positive, the y value of the function is negative infinity. That means is x gets bigger, the y value also gets bigger, but it gets bigger down the way, right? Negative. Now, on the other extreme, the limit as x tends to negative infinity, this function becomes the limit as x tends to negative infinity of negative 2x cubed. What's that going to get me? It's going to get me negative 2 times negative infinity cubed. Well, negative 2 times negative infinity cubed. Negative infinity times a second negative infinity times a third negative infinity gets you negative infinity. And a negative thing times another negative thing makes the answer positive. Positive infinity. So there's your two in behaviors. What that's telling me is that as x gets extremely big and negative, the answer, the y value, goes up. So my best guess is that that's probably a very basic shape of what that cubic is going to end up looking like. So it's in behavior. Now, let's add some more information. We are now going to talk about the zeros of a polynomial. Basically, the zeros of a polynomial are the x coordinates of the x-intercepts. So imagine I have a polynomial that's already factored. And really, to answer the zeros of a polynomial, you need it to be factored. If the polynomial is not factored, then you've actually got to do some algebra and factor it for it. Now, if you want to find out the x-intercepts, which is what we are going to do, we have to solve when is the function equal to 0, right? So for what values of x do you get 0? And because it is factored, we can get the answer 1 from each factor. This guy is x equals 1. This one is x equals negative 3. And this guy here is x equals 2. And I'm going to introduce a new term. It's called multiplicity. And multiplicity is essentially how many times does x equals 1 give you an x-intercept? Well, it's pretty clear here. There's 1. But let's just pretend that that was 2 and this was 3, right? So it's x minus 1 times x plus 3 squared times x minus 2 cubed. These values of x are not changed, but the multiplicity is. The multiplicity of this one, let's just call it m, is 1. The multiplicity of this one is 2, and the multiplicity of that third one is 3. Now, how does multiplicity play into the sketch of a polynomial? Well, if I start off and look at this guy, I know that to x equals 1, we have an x-intercept. At x equals negative 3, we have an x-intercept. And at x equals 2, we also have an x-intercept. I'm going to make these a little bit more bold. There we go. But the problem we have about x-intercepts is that it means that it crosses the x-axis, right? That's pretty much it. But there are two ways in which that can happen. Imagine that's our x-axis, right? Here's our y-axis. And I happen to have an x-intercept at, say, 5. I could get an x-intercept where the curve cuts it like that. I could get an x-intercept where it cuts it like that. Or I could get these last two situations. I could get an x-intercept at 5 that goes like that. And I could get an x-intercept at 5 where it does that. Each of these are possibilities. Right now, I only know what or where the x-intercepts are. What I don't know yet is which one of these 4 versions are we going to end up with. Is it going to look like that as an x-intercept, this, that one there, or that one there? So here's a term. When an x-intercept, when the graph that cuts through the x-axis looks like either of these two, we say that that is an example of crossing the x-axis. So we could say the 0 of the function crosses the x-axis, or we could say the x-intercept, if you prefer, crosses the x-axis. In these two situations here, right, so that's, these two are both examples of crossing. In these two here, we say that it touches the x-axis. So how does multiplicity tell us whether it's a cross situation or whether it's a touch situation? Well, it's actually quite simple. If the multiplicity is even, like 2, 4, 6, then the 0 or the x-intercept touches the x-axis. If the multiplicity is 1, 3, 5, then we say that it crosses. So on my diagram here, at x equals -3, I know it touches. At x equals 1, I know that it crosses, and at x equals 2, it crosses. So far, so good. Now I'm going to take this fella and I'm going to find the degree of the polynomial. And if you think about, if you think about what you would get if you multiplied that out, it would take you forever and a day to do that. But to get the degree, I only need to know the biggest power of x that you would eventually get out of this combination. Well, x for the first one, x plus 3 squared would get you x squared, and x minus 2 cubed would get you, amongst other things, x cubed. But the biggest power of x from each of them is 1, 2, 3, as you can see, and that gets me x to the power of 6. And so I know that the degree of this polynomial is 6. You can also use multiplicity to come up with the same answer. Multiplicity of 1, multiplicity of 2, multiplicity of 3, since these are linear terms at least, 3, 2, and 1. Multiplicity is 6. Or sorry, the total multiplicity is 6, so the degree is also 6. Now I can use end behavior. The limit as x tends to, let's say, negative infinity, and the limit as x tends to plus infinity. What do you get? You get the limit as x tends to negative infinity of x to the 6, which is negative infinity to the 6, which is plus infinity. And this one will be the limit as x tends to positive infinity of x to 6. And that's infinity power of 6, which is also plus infinity. So I know that the end behavior is as x gets really big, it goes up the way. And when it goes this direction, it goes up the way. Now, if you put together the three x-intercepts, and the multiplicity now tells me if it touches or crosses, and you add on top of that the end behavior, if you put these things together and you realize that all polynomials are basically just wibbly wobbly curves, it has to touch. So that means it has to go like that. Then it has to get to here. So that means it's going to have to curve and cross. But then it has to get to here and crosses. So it has to go up and do that. So we have basically got a very simple sketch of what a polynomial looks like based on its multiplicities, its zeros, and its end behavior. Do one more of those things. Suppose I'd like to get a sketch of that guy. And I'm talking about a really basic sketch, something that looks like this, not particularly detailed, but the basic shape with the structure of what it would look like. Well, I would look at this guy and I'd say, okay, then let's find the zeros. There's one at -3. There's one at 1. Let's do the multiplicity. 1 and 2. So that makes this polynomial a degree of 3. Okay. Which basically means it behaves like x cubed. So end behavior now. The limit as x tends to, say, infinity of f of x is going to be the limit as x tends to infinity of x cubed, which is infinity cubed, which is infinity. And the limit as x tends to negative infinity of f of x is the limit as x tends to negative infinity of x cubed. And that's negative infinity cubed, negative times negative times negative, and you get negative infinity. So, and I almost forgot, this one will cross the x-axis, right? This is 0, and this one will just touch the x-axis. So, at x equals 1, you have a cross, and I'm saying that at x equals 1, I should say. At x equals 2, you have a touch. And at x equals -3, which is here, you should get a cross. Okay. Now, what's the end behavior like? As you get the extreme values of x, it goes up the way, so it's up here. And going negative x's, going this direction, you get negative infinity, so it is doing that. And now I'm trying to put the puzzle together. Well, you have to cross. Then you have to get to this x-intercept, so I'm going to have to curve. But it's a touch, which means I'm going to just bounce off and then go up. And there is my sketch, a very basic sketch, but at least it gives you an idea of what the thing looks like for this particular polynomial. And that is